Alright, this is video 3 for the forces unit notes. This will be the final video for this section. In this one we're going to look at springs and elastic cords. Now again, this will be another great example for Newton's third law, because what a spring does is it acts as a medium for two objects to interact. So here I have object 1 and object 2, and these two objects are going to interact through this spring. Notice this makes a system, this object 1 and 2 system. So these forces then here and here are internal forces within this two object system. Therefore, it satisfies Newton's third law. These forces will be equal in strength and opposite in direction. And these will be elastic forces. And notice that these forces then, again, will have the same strength because it's the same spring attaching the two objects, and they're opposite in direction, acting on two different objects. They're internal forces within a system. All of that supports Newton's third law. What's interesting about springs is that as you pull back on them, they pull back on you with an equal force. And as you pull them further from their rest position, the force becomes greater. So it's a variable force. The force changes with how far you pull or compress a spring. Eventually, though, you can damage a spring if you pull it so far it will no longer return to its rest position. Okay, now one of the activities I'll give you will be to actually make this graph. So if I were to make a graph, force versus displacement. Now, what I mean by displacement, if I have a spring hanging, I'll put a little hanger here, from here to here, I'll call it X, will be our rest position. So I'll call it X naught. If I were to place a weight on it and stretch the spring out, I'll call this X. That would be my final position. All that I'm interested in, though, is from here to here. This is my delta X. It would equal my X minus X naught. So it would be the final position minus the initial position, and it has to be this way. We have to look at its displacement, not its overall length. So if I were to make a plot of this, if I were to keep track of how many newtons of force I'm placing on this spring, and keeping track of all this, I would find something that looks like this. And what this would be then is a linear relationship. I don't like that line. That's a better line. Okay. Now, looking at this, because this is a linear relationship, and again, I'm going to have you do this with your own spring just to prove that it's a linear relationship. I'll give you a spring, some weights, and some graph paper. What that means then is that this elastic force equals, well, I shouldn't say equals, is proportional to the displacement. Now, the reason why I can say that is if I were to draw a free body diagram for the weight. So this is a free body diagram right here. Put an X and Y axis on here. The amount of weight I put on it would be a gravitational weight, which, remember, is m times g. Opposing that would be an elastic force. Now, if this is in equilibrium, that means that the sum of forces on my y-axis would equal the elastic force minus the gravitational force. Well, if it's in equilibrium, it should equal 0. So hopefully you can see that. Which means then that the elastic force equals the gravitational force as long as it's in equilibrium. So that means as long as it's not accelerating. And we talked about equilibrium before. So when I plot my force here, even though I'm using gravitational forces, it's the same thing as the elastic force. As long as it's not bobbing up and down, it's in equilibrium. So the elastic force needs to be proportional to the displacement. And this is what we call Hooke's law. Now, with this, then, we can see that the elastic force, it has to equal then some constant times delta x. And this constant is our constant of proportionality. Now, forces are vectors, and so are displacements. And notice that when the displacement is negative, pointing down, the elastic force is pointing up. So what that means then is I have to have a negative in this to help take care of the direction. If I push a spring to the left, the force would be acting to the right. If I pull down on a spring, the force would be pointing up. So we have to have that negative sign in there to always reverse the direction. Now, looking at this, I hope that you can see that this k here then, because it is the constant of proportionality, would have to be the slope of the line on our graph up here. So let's go back and take a look at our graph up here. Forces are measured with newtons. Displacements are measured with meters. So the slope of this line, well, let's rise over run. It would be the force over displacement, or the units would be newtons per meter. And that is what our spring constant is. If we take a look at this, again, just doing some quick calculations, notice how k would be a force over a delta x. So that'd be the same thing as the slope of our line, a newton per meter. So k would be the slope of the line. It would be the spring constant. It measures how stiff the spring is. So stiffer springs would have a larger value for k. Weaker springs would have a lower value. So a rubber band would have a very low value of k, and the front coil springs on a car would have a very high value for k. Now, slope is just half the picture. The next thing we would have to look at is area. So if I looked at area, think of like length times width, that would be like a force times a delta x, or a newton times a meter. We will learn later on that a newton meter, or a newton times a meter, is the same thing as a joule. It's energy. So the area under this line would give us how much potential energy, how much energy is stored in the spring because of it being stretched or compressed. We'll take a look at that in greater detail later in the year. Okay, so the minus sign, as I said before, is to change direction. And that's because elastic forces are what we call restoring forces. They are trying to restore the spring to its rest length. And that's going to become important when we talk about oscillatory motion, things bobbing up and down. All right, finally, let's take a look at a graph here. This is the same, force delta x graph. Hooke's law only works up to a certain point, right about here. And this is called the elastic region. Once you pass a point, you enter something called the plastic region. That's where you stretch a spring so far that it no longer returns to its original length. If you continue to stretch it, we get fracture. That's where the spring will physically break. So when we look at Hooke's law and how it is a linear relationship, it's only linear during the elastic region. Once we pass this point, Hooke's law no longer works. Well, that concludes this unit's notes. Ciao.